So my name is Strzebonski. I will be talking about mathematical function properties. So that talk is about functionality that's planned for version 12.2. So nothing of this is in 12.0 and will not be in the nearest release. So we have added three types of mathematical function properties. So set theoretical properties. So we'll have functions like function domain, function range. Actually, those functions are already in Mathematica. We have extended them. So now they work for a larger number of functions. And new functions are injective function C, surjective function C, and bijective function C. So what's the C? That's something new. So we had some functions that ended with Q and returned true or false. But in this case, C stands for condition. So we may return condition for the function to be injective or surjective. And in case we may also not be able to decide whether a function is injective or surjective. So if it's false, it means the function really is not injective, for instance. If we cannot tell, which of course always will happen for some functions, then we just return unevaluated. So that's why we changed the design from Q at the end to C at the end, that Q at the end will always return true or false. So, and then there is a series of topological and analytic properties. So function discontinuities, function singularities. We'll give description of the singularity and discontinuity set. And then we have another three C functions, continuous function C, holomorphic function C, and meromorphic function C. And finally, the sign properties of real functions, or that's how I called the group. So it's function sign, function monotonicity, and function convexity. So in a sense, they are sign properties, since at least for some function, monotonicity is the sign of derivative, and convexity is the sign of the second derivative. So in this sense, they're also order-related properties, so that's where the sign comes in. So the first new function, injective function C. So a function that goes from x to y is injective if for any y in y, the equation f of x equals y has at most one solution, x in x. And equivalently, the function is injective if for any two different points, the values are different. So for instance, we can evaluate injective function C for, what happened here? For exponential, and it's an injective function. We can plot the exponential, see that there is at most one solution for every, so each horizontal line intersects the graph at most one point. Then we check whether a quadratic function is injective. It's not. And we can see that there are some horizontal lines that intersect the graph in more than one point. Now the injectivity depends on the specification of x and y. So we usually say that the function is injective, but actually, we mean the function, we actually have to say what x and y are to know. So here we specify the set x is complexes, and now exponential is not injective anymore. So by default, if we don't specify the domain, it's reals. And if we say quadratic function, but now we restrict the set x to positive values of x, then quadratic function is injective, because we are looking just at this part, the right-hand side part of the parabola. And we can also restrict the codomain, the set y. So we are looking at injectivity of the function x cubed minus x, but only for the set on which the values are greater than 1/2. So we change the set y here, and if we look, values are greater than 1/2, so it's above this line, and then the function is injective. If over the whole reals, it's not.
What's the difference between injective and monotonic? It looks like they're kind of the same.
Well, for univariate function, yes, it doesn't have to be univariate. Doesn't have to be real. If it's complex, then yeah. Actually, yeah. And the main method for deciding injectivity of univariate real functions would be just called monotonic. But but yes.
How do you figure these things out without having to do some kind of global search? I mean,
So
the idea behind how you figure out if something's injective, for example?
Well, the most general and the slowest method would be it's a quantifier. It's a quantified statement. The definition of injectivity, we can eliminate the quantifier if we can. Then we get the solution. Then of course we have certain properties of certain function. We have collected properties of functions, so we know which specific named function is, for instance, increasing on some intervals, on some such, and then we can use we can combine those properties with, we know how it combines for composition. For instance, composition of injective functions will be injective, and this kind of stuff. So that's the other method. That's the fast method if we can get all the information. And here's injectivity with symbolic parameters, and we can see the nice new conditional expression formatting. So this function is injective if the condition is satisfied.
Question: why return a conditional expression as opposed to just the condition?
Because we only know that it's true if the condition is satisfied. We don't know that if it's not satisfied. It's not a necessary. It's not a necessary condition. It is a necessary. Wait. It's a sufficient condition, not a necessary condition.
Okay.
And we have a mapping. So it's a mapping from R2 to R2, and we prove that it's injective. This one, of course, is very easy to decide. So we can solve for x and then solve for y. And here's a full syntax. So the injective, surjective, and bijective function will all have the same syntax. So it's the functions. So it's either one function or a list of functions. Then conditions on x, conditions on y, x variables, y variables. So the variables in the domain, variables in the codomain. And then there is the domain in the sense reals or complexes. There are just two values for a DOM, whether it's a real function or complex function. And the actual mapping that needs to be injective is the functions that are restricted to this set. So S is the solution set of conditions for x. T is the solution set of conditions for y. And we take intersection of S with inverse image of T. And a mapping goes into T. So the solutions of y coordinates, and that's where the mapping is supposed to be injective or surjective or bijective. It's the same syntax. So now let's look at the bijective, surjective. So the function is surjective if for any y in y, the equation f of x equals y has at least one solution. So exponential function is not surjective because the non-positive values are not attained. And for instance, tangent is surjective because all values are attained. And surjectivity again depends on the specification of sets x and y. So if we specify that we want exponential, but only on the set of positive x's and into the set of y greater than 1. So we are looking as a mapping from this positive x into y greater than 1, then the function is surjective. And on the other hand, if we look at tangent over the complexes, then it's not a surjective function, because we can check it with function range. I and minus I are not in the range of function tangent. So now if we restrict ourselves to the set without this I and minus I, then tangent is surjective. And here's the full syntax. It's the same as for injective function. And now bijective function C. So the function is bijective if the equation f of x equals y has exactly one solution. So it's both injective and surjective. So here is a function that's bijective over the reals. We can plot it to C. And indeed it's a monotonic function since it's a univariate real function. So bijective is the same as monotonic that covers all values. And tangent is not bijective because it's not injective. But now if we look at the first function over the complexes again, if we specify x and y differently, first function is not bijective over the complexes. On the other hand, because it's not injective, and tangent is a bijective function if we restrict it to a single period. Oh, the algorithms for this? Yeah. So again, the fallback algorithm is write everything as quantified formula and eliminate the quantifiers, basically. The easier algorithm we have, again, we have certain database of functions and values that they attain, so we can analyze it and then you use some rules of how it carries through function composition to decide, hopefully. Again, this is the fast method if we can do that. Otherwise, we have to do some computation, which usually is. Then there are some criteria for, say, complex function that has essential singularity. So we can use Picard theorem so that in every neighborhood of the singularity it attains each value except at most one infinitely many times. So we know that the function, for instance, is not injective. So that's one of those criteria like that. We have a bunch of things like this also built in. Okay, so now slightly different family of functions. So function, yes, please.
If I had some code already that for polynomial functions uses resolve to determine injective, I have that code. Should I rewrite it with injective function C? Will it run quicker?
Hopefully. Well, one thing is that the implementation is not quite finished yet, but so this part is actually not written yet, the polynomial, but hopefully, for instance, we may put some stuff into the cylindrical decomposition algorithm so that it ends earlier if it decides that the function is, for instance, non-injective. Finds in one fiber, finds 2 points, then we are done. We don't have to compute the rest of quantifier elimination. So it might be faster than. So you can put element integers in the condition, and in some cases it will work. It's harder than.
Yeah.
So function discontinuities, it will give a condition such that the function is continuous outside the solution set of the condition. So in particular, the condition will also contain, or will be also true for all the points where the function is not defined. So discontinuities of floor, here is an encoding of integers as an equation. Discontinuities of tangent log x, so that here over the complexes, so we have, this will be the branch cut of log. This is the points where tangent is not defined, and x equals 0 came out of the branch point for log. Yes?
In the discontinuities of floor, why didn't it just give you the set of integers instead of?
Oh, we try to return everything as equation, an inequality rather than domain condition. It could say element x integers, but yeah, just to be sort of consistent between all the. So it's always equations and inequalities.
I'm following up on that. Since this is still experimental, a strong case could be made that should be a set of integers, in my opinion. That's just strikes me as harder to understand than
Right.
sine pi x equals 0.
Yeah, possibly.
Just 2 cents.
Oh, so the counter argument would be if you have composed function, then you would get the sine of pi, whatever the inner function of this was, like floor of I don't know, log x. What would happen here? You get this inside the sign, and then you would get condition that some complicated expression is an element of integers, which sort of none of our function would handle anyway. So it will be dead. And here we have some hope that say reduce will do something with it. One could also argue that reduce could handle the integers statement, but.
Floor of x, you could use reduce on the result that to get the integers out.
To get the solved version of the condition. So this is a very fast function because it just collects all the information from knowledge of discontinuities of all the built-in functions. So as you can see here, it's just collected the knowledge of discontinuities of logarithm and of tangent. So this function takes no time. Now, if you want to solve it, of course, it will take a bit of time. So this is just a structural function.
One more.
Uh-huh.
I think output should have the same design. In input 27 has x equals this, or this, or this. And in previous, you produced sinus pi x equals 0, its equation.
Yeah.
Wrong.
Which one's wrong?
No, design should be in form x equal pk, something like this.
X equals.
X should be in output, not sinus x pi.
Oh, parametric solution. But again, that would.
In 26, go back.
Oh, yeah. Here?
So I think he's talking about before you change it to log of x, when it just says sine of pi x equals 0.
So that instead of integers,
Right.
have parameterized thing?
Yes, here.
Yeah, but you
Should be floor x and you solve. You produce output in form sinus.
Yes. Okay.
I think
It's wrong.
What's wrong with it?
Wrong because it designed wrong. It should be solved. Sine pi x equals.
Okay, so that's what I just explained. So if you get it solved, then the first thing is that it's not that useful for applying somewhere else as a condition because it will have additional parameters. And second, you add huge time to the computation. If you can always get the condition, and if you want it solved, then you can apply reduce to it or solve to it or something. Then of course it will take many orders of magnitude, usually time-wise, more to solve it than to generate the condition.
And just to clarify one point, I mean, we want these functions to be very fast so that we internally can use them in our other solvers, and that people who build on top of the system and not have to, put a time constraint around every single one of these, like you do if you're calling reduce or solve.
So, well,
This is a question in a different direction. So I'm curious what your definition of discontinuity is, because we've been working in alpha on some resource functions that are very similar to this, and we ran into the issue of something like, because it works in a very similar way, and we ran into some issues where we would look at something like square root of 1 plus x, right? And looking at it in sort of the nesting of continuities, or maybe not square root of 1, maybe square root of 1 over x plus 1, right? Where the discontinuity of the rational function is not actually in the domain of square root of x. So I'm curious how you've handled those kinds of things and what this would return.
so basically, that's the next thing. So the solution set is so discontinuity is not minimal. So the function is guaranteed to be continuous outside the set. Doesn't mean that everything in the set is a discontinuity. So we just collect all the discontinuities of all the functions involved. The resulting function may not have discontinuities. So for instance, so that was the next example. So if we plot this function, so we produce discontinuities of unit step and gamma, but actually the function is continuous, it so happens, because they cancel.
So it should actually be named opposite, because it gives sufficient position for continuity. It doesn't give the list of discontinuities.
Right, or it gives a set that contains all the discontinuities, but it may contain more.
But solve doesn't show the solution. Solve doesn't return things that are the solution. The result of solve contains the solution.
Yes, so in this case, it just contains the solutions, yes, not.
I guess he wants it to be called possible function discontinuities.
Yes, that will be possible, yes. And I'm running out of time, so.
I know, but from what users ask on the alpha website, they want exactly that discontinuity.
Right, so that's a much harder situation. You can take the function discontinuities, and now you would have to check hope that it's a finite number of them, and then check for each of them limits or something to say that it's actual discontinuity.
We should talk, because we have that.
Right. Right. So this is more useful for determining the function is definitely continuous outside of this set. So function singularities. Now I'm really running late. So the function singularities is a function similar, but the function is analytic outside the solution set of the condition. Again, with the same caveats that we may get too large set. It's a collection of all singularities of all functions involved. So let me make it faster. So continuous function C. This will test whether a specified function is continuous. So here is this function. And so it's one point to make is that it's a continuous and defined everywhere, and it's not continuous in the sense that it can be extended, but the actual expression we give is continuous, so it's sine of x by x is not continuous at 0 because we don't define what it is at 0 if we just say sine of x by x. If we say that it's a piecewise function that outside 0 is sine of x by x and at 0 is 1, then it's a continuous function. And if we put a there, we'll get a condition saying that the function is not continuous unless a is 1. And here is a multivariate continuous function with condition restricting the domain in which is supposed to be continuous. So the syntax is functions, constraints, variables, and domain, which is real complexes. And we have similar to functions, which I will just mention, holomorphic function C, which tests whether the function is holomorphic, or real analytic. And we have meromorphic function C, which tests whether the function is meromorphic or locally a ratio of real analytic function. I don't think anybody talks about real function being meromorphic, but it also works over the rails. And it means that it's a locally ratio of real analytic functions. Now function sign gives the sign of a function like that. If the function doesn't have a fixed sign, it says indeterminate. And it has an option strictness. So x squared is not strictly positive, so it will give indeterminate. And we may get a condition for function sign, and this is larger condition, so we need to unpack it to see what it was. And similar function, we have function monotonicity. This one is only for univariate functions, so it's slightly different syntax than the function sign. So function sign can work for multivariate function monotonicities. For univariate, again, can be strict monotonicity, weak monotonicity, and convexity. Convexity can be a multivariate function, can be convex. So, for instance, here is a convexity of a multivariate function. And that's what the function looks like. Okay, so now the comment about methods that I already made. So there are three types of methods. So there is a collected information about properties of mathematical functions. Then we use closure properties to try to derive the properties based on this collected information. And then there are fallback computational criteria that actually require solving equation and inequalities and quantifier elimination that are much slower than the first two methods. So this is all that I have. Thank you.